Welcome back. This is Code Dive 2021 and our next speaker is Maciej Norberciak. Maciej works in Nokia, where he's primarily a software architect, but also trainer and mentor. He holds a PhD in computer science, specializing in artificial intelligence. Throughout his career, he's worked in the telecoms industry, taking part in projects on various embedded platforms as a programmer, designer, architect, and project manager. His hobby is learning new things, whatever they are. So today, Real-Time Systems 101. Maciej, you like learning, but this time teach us something new, please.
Thank you. Hello, everyone. If you are a Code Dive veteran like me, you probably have noticed that we don't do just those hardcore, highly specialized code diving lectures here. We also do some popular science, like life of an instruction inside the processor, or how the different kinds of memories cooperate inside the computer. This particular talk is sort of spiritual continuation of my talk from last year about embedded systems. You will see in a moment that many real-time systems are actually embedded. But before we go to the meat, let's think what real-time means. If you ask someone what's real-time, what does it mean that something happens in real-time, the first answer you will probably get is something like, well, it happens very fast. So a system that is a real-time system must be highly performant. Is it right? Not necessarily. You see, there are incredibly powerful supercomputers that are not performing any kind of real-time computation. At the same time, we have some low-tech, small, weak computers that are actually real, nomen omen, real-time systems. Okay, so the speed and performance is not the key here. So what's real-time? When something happens in real time, maybe it happens live, like live concert or live football match. Let me tell you a story. I was watching World Championship football in Korea and Japan on Czech TV, because it was almost impossible to catch any games in open TV channel in Poland. Fortunately, I had live audio commentary in Polish radio. Both events were live. Both streams were live. But there was this slight time difference between the audio and vision. The guy on the radio was already screaming, "Goal!" and the people on the screen were still playing. Both events were live, but were they real-time? Not really. They were near real-time. And this nebulous term in computing and telecommunications means that there is a time delay introduced by processing of an event or transmission delay, like in my case. And there is a discrepancy between the event occurrence and actual result, in this case, showing on the screen or hearing on the radio. This near time, a nebulous term, I must admit, implies that this discrepancy is not significant. But not significant, what does it mean? It's 1 second, 3 seconds. My point here is that your mileage may vary, it depends. Before we define real-time properly in computer terms, let's think about other categories of computer systems. You already intuitively know that this has to do something with time. And historically, the first category of systems were called batch systems. In batch systems, you don't mind where the result from a computer arrives. Of course, if they arrive within reason. The time taken might be hours or even days. You define a job, you submit it to the computer, and after a few centuries you get an answer, and the answer is always 42. Actually, the term comes from 1960s, when someone has noticed that you don't have to submit tasks to your computers one by one. You can have a programmer program them on a punch cards, and then a card reader will store a batch, a set, a group of jobs on a tape drive, and then the operator can take this tape drive to an actual computer, which will do the computation, produce an output tape, and operator will take it to a printer, which will print out the results. And by the way, this incredibly sexy picture comes from the actual instruction manual of the IBM computer system from 1959. Back then, only a male could be a programmer, and an operator was always a woman. And look, we have an actual spooler here. We store input and output on an actual physical spool. If you are ever wondering why your high-tech printer has something called spooler. Anyway, batch systems are not something you interact with all the time. Right now, most of the systems are so-called interactive online systems. And you do interactive online when you are accessing, for example, www, World Wide Web. In interactive online system, you expect results to arrive in fairly short span of time, couple of seconds usually. And you define a task, you submit it to the computer. This is probably some remote system and has many users and does some clever time slicing to service them all. As the load on this system builds up, this system inevitably slows down to the point of completely stopping. This is not acceptable in time-critical situations. When you are doing something time-critical, you need a real-time system. Like when you do cruise control in your car. You dial in the desired speed, and your car computer does some clever computations, comparing this desired speed with actual speed, and then sets a set of control signals to your car engine unit in order to accelerate or brake as necessary. If this control operation, this computation is performed in a timely manner, this will result in a smooth operation of the vehicle. But if results are calculated late with delay, you will have this choppy, kangaroo-like movement, and this system is worse than useless because it degrades your car performance. And if you have adaptive cruise control, it's even worse. You have a radar or LiDAR input, and you have to factor it in. You need to brake when you see the vehicle in front of you. If this calculation is not performed quickly enough, if it's late, you're dead or injured, or at least very unhappy. In real-time systems, you have to react on an external event, on stimuli, and you have to deliver your results in a defined amount of time. The correctness of such systems operation depends not only on the logical result, but also on the time it was delivered. Failure to respond is as bad as wrong response. This defined, specified time period where you have to respond is called deadline. And in general, in real-time systems, deadlines matter. But before we go to different kinds of deadlines, let me show you some examples of real-time systems. They are practically everywhere. There are in cars, of course, in pacemakers, in planes, in things that shoot planes down, in ships and spaceships, all those beautiful computers, right? Well, wrong. You see, all those systems I've shown are computers. They do computerish stuff, but they perform a dedicated function, like flying or sailing. And they are parts of bigger systems. They are embedded. And here's this promised relation between real-time and embedded systems. Embedded systems are systems that are built for purpose, built for application. And they comprise of hardware, software, but also from other parts, like mechanical parts, hardware parts, in order to perform a dedicated function. That's why when you are looking for information on real-time systems, you probably end up with a book entitled something like Real-Time Embedded Systems. Okay, but let's go back to just real time. I mentioned the deadlines and that the deadlines matter. And the deadline that matters the most is called hard deadline. In hard deadline real-time system, your system stops working properly if the deadline passes, if you delivered your your answer late. It's like production line. If you miss your spot on the production line, well, your production line stops. It doesn't work. The same situation we have in airbag control system in your car. If it explodes just a fraction of the second after this split moment it was supposed to explode, well, it doesn't matter. Your system doesn't work. You are in trouble. Quite often we associate a utility function with the response of the real-time system. This is a function over time. We get an event coming and we define a deadline. Within this deadline, we have to service this event somehow. And till the deadline, the value of this utility function is positive. But the moment the deadline passes, in hard deadline system, the value of utility function goes down to 0. Fortunately, there are real-time systems that are less demanding in terms of deadline. We call them weekly hard deadline systems. Bad news, we have still plenty of deadlines and plenty of hard deadlines in such systems. Good news, we don't have to satisfy them all. In weekly hard deadline system, you have to satisfy a set of hard deadlines out of all hard deadlines. And those are typically some kind of feedback control systems where you can get away with missing a few control points without doing something catastrophic. Those are also systems which have to deal with some kind of failures, like systems which operate in harsh environments, within the presence of electromagnetic interference, like systems that have to operate in space. This is Parker's solar probe. It's hard to imagine an environment that is more electromagnetically active than corona of the sun, and this is the probe that is supposed to examine the sun from a very short distance. And it's doing it successfully. It's a real-time system, and it's a weekly hard deadline system. But again, this is an extreme example. Normally, we do things a little bit more relaxed. We do things like firm deadline systems. In firm deadline system, you still have a hard deadline, and your answer is still useless after the deadline passes. But it's tolerated. On occasion, every now and then, you can miss your hard deadline, and nothing catastrophic happens. Okay, the quality of the service provided by your system goes down, but your system works in principle. Like your car engine unit. If it misfires, every now and then it's tolerated. Okay, your car engine power goes down, your fuel consumption goes up, but it's not like it explodes immediately. If your pacemaker misses a beat every now and then, well, the patient is still healthy and alive. Of course, if your pacemaker misses a beat repeatedly in a short succession, it has to be turned off. And those systems are designed in such a way that if they experience a permanent failure, they turn themselves off, as not having a pacemaker is better than to having a faulty one. Fortunately, most of the real-time systems we have to deal with are soft deadline systems. And one could argue that every single computer system in the world is actually a soft deadline real-time system. In soft deadline real-time system, your answer is less useful after the deadline. If you deliver your answer after the deadline, it's still okay, your quality of service goes down, the system does not experience anything dramatic. If your seismograph misses a few data points, it's okay. If your sound system misses a bit, it's okay. If you missed Halley Comet transfer, it's okay, there is another one in 75 years. You see, this all boils down to some temporal requirements. In soft deadline system, when you define a utility function, it's positive till the deadline, but it's not like it's falling to zero after the deadline. It's falling, but not as fast and not necessarily to zero. The deadline is the most important temporal requirements we put on the system, the response time. All required responses in real-time systems are time critical, although this time may vary from microseconds to days. And the designer of such a system should be able to predict the performance delivered by the system. But even with best education, goodwill, and experience, sometimes it's impossible to give you 100% guarantee. This is complicated because there are two ways in general how the tasks are processed by a computer. First case concerns the demand to run jobs at predefined intervals. Those are so-called periodic tasks. You have a period defined a priori, you know it in design time, in which particular task has to run. And your system is purely time-driven. It's like monitoring condition of an ICU patient. You take the temperature measurement or O2 blood saturation every 1 minute, 5 minutes, 5 seconds, every defined period. But your patient's condition may deteriorate rapidly in an unexpected random moment. And this is this case 2. Case 2 concerns the situation where you have to deal with an event and you have to run a periodic task. This is no longer time-driven, this is event-driven. The characteristic of inter-arrival pattern between events is not known during design time. It's purely probabilistic. And it's hard sometimes to predict such a system's performance. You have to respond still to an event. You have to save your patient if his condition deteriorates. But you have to take into account that you never know when something happens. Okay, sometimes you know, or at least have some information on this arrival pattern. You have sporadic tasks which are still aperiodic, but at least you know this minimum inter-arrival time between events. But in general situation, you are in hell because you have to deal with mixture of periodic and aperiodic tasks with unknown characteristics. But this is not all. This is just one type of constraints we have on tasks in real-time systems. Time constraints, deadlines. But there are others. We can be resource constrained. We are a part of a larger whole. We have resources like CPU time, memory, some hardware devices, and we either have to share them with other processes or we need to manage our exclusive access to those resources somehow. You know, when you are writing in the memory, normally there can be just one task, one process writing, because you will get inconsistent state otherwise. Energy is also a factor. If you are in embedded system, you have most likely some power source like battery or engine or nuclear reactor perhaps. You have to manage this energy responsibly. Task precedence is quite popular. You know, when you are driving a stick-operated car, in order to change gears, you have to press the clutch, wave the stick, changing the gears, and depress the clutch. And it's not like this order of doing things is, you know, voluntary. You have to do it in exactly this order, period, or you destroy your car. And as those systems sometimes operate in harsh environments and in harsh conditions, or have to operate for a very long time without any repairs, they have to be fault tolerant and they have to be reliable. This is all very complicated. This is all very hard. And you need some knight on a white horse that will solve all of those problems for you. I will give you a horse now. Well, it's not exactly a white horse, it's a gray donkey, but you get the picture. This horse is called operating system. An operating system is a software set of services that allow you for running and execution of tasks, allow you for controlling of tasks, allow you for hardware and resource management. I will not dwell into details on operating systems. If you're interested, you should buy this book, read this book by Zilberschatz, Gavin and Gonie. This is a Bible on the matter. You need an OS, but not just a garden variety OS. Traditional, or so-called traditional OS does not guarantee the timely execution of tasks, because traditional OSs have a lot of background processing, like garbage collection or whatnot. They do things in background and they do them in unexpected moments, so they are completely unfit for real-time applications. In real-time applications you have to be able to predict when your task starts and stops. You need a real-time operating system, RTOS. And real-time operating systems are multitasking systems designed for purpose of real-time operation. Usually they are embedded systems, and usually the ability to predict the performance of such a system is much more important than its optimization. But there is a caveat. Those real-time operating systems do not guarantee anything by themselves. They give you a set of proper tools to write a system that is supposed to be a real-time system, but they do not give you any guarantee. So coming back to our horse and knight metaphor, they give you a horse and maybe an armor and a sword, but you have to be a knight by yourself. Well, this multitasking was bolded for a reason, because this term cries for definition. Multitasking is doing multiple things at the same time. Ta-da! Well, obviously, you sit at your PC, you're watching me in one window, you're playing League of Legends on the other window, and you are checking the time to finish every now and then. Your computer is doing at least 3 things at the same time. Yes, you would say. Yes, Maciej, my computer does parallel execution because it has 4 cores, it's a modern one, and I still have 1 core left for playing music. Let's play some music. No. You see, multitasking, even in modern multi-core, multi-processor system, but also in old single-core, single-processing Unix system, does not require parallel execution. What it does, it's a clever trick called task switching. So the operating system is giving the processor time to one task, and then takes the processor away and gives it to another task. And again, and again. And this trick is performed so fast that you are not able to notice. You have this illusion of parallel execution. This multitasking scheme can be either cooperative or preemptive, and we'll handle those topics next. But in general, real-time operating system must support a scheduling method that guarantees response time, especially to critical tasks. So task must be given some priority. And we will also be talking about giving tasks proper priority. But let's go to the multitasking. First multitasking scheme is called preemptive. That means that the operating system, the part of it that is called scheduler, takes the processor away from low priority task when high priority task is ready to run. And high priority task runs, the low priority task is preempted. And preemptive multitasking in general is good, because it guarantees a short response time for high priority tasks. if you have defined something as high priority, immediately when this task is ready to be run, when low priority task has a processor, it's preempted and high priority task runs. Preemptive multitasking also gives you a higher utilization of the processor. And this is in general desired if you are designing a system. You don't want to have your system idling all the time. It's waste of time, of resources, you're just wasting money. You build your system too big. But this is not the silver bullet. There are disadvantages to preemptive multitasking. Namely, it's harder to analyze with all this task switching. And task switching comes with a price. This price is called preemption delay. There are a set of operations you have to perform before you take the processor away from one task and switch to another task. And as if you have multiple task switches in quick succession, this preemption delay starts to build up and starts to matter. All right, so if it's hard to analyze and bad in general, I've mentioned this thingy called cooperative multitasking, right? So in cooperative multitasking, you don't have preemption. You don't take the processor time brutally away from the process. Process gives the processor away voluntarily. Every task has some moment defined or a set of moments where it can switch to another task. This results in fewer task switches, but it also results in increased latency for high priority tasks because high priority task has to wait till the task currently using the processor gives the processor away voluntarily. It's okay. But in general, it depends on your system context whether you can double in cooperative multitasking or not. But there is one last thing. I said that the hard part about real-time systems are events that come at random. So why not do a system that is purely event-driven, event-triggered? There are such systems. Like that. Ta-da! This is F-16 fighter plane. And it is equipped with digital flight control system. And originally, this digital flight control system was a purely event-triggered system. And I encourage you, after this talk, Google F-16 DFCS problems. As this aircraft is quite old, those reports on problems are already public. And it's an amusing read, really. You will find out that some phrases and words repeat all over those reports. And those words and phrases are random, unpredictable, and untestable. You see, in order to test an event-driven system, you have to test properly, of course. You have to test every possible combination of events coming in every possible time relation. And if your system is simple, just a couple of events, it's okay, it's doable. But if your system is as complicated as a fighter plane, it is impossible and untestable. The most common problem in F-16 DFCS was failures that were results of events coming at random and required reset by pilot. You know, the system crashed and you have to turn your aircraft off and on again. Power cycle it, sometimes in air. This is not something you want to do with a plane in general, especially if it's a fighter plane. So if you want to design an event trigger system, it's fine if your system is simple. If it's a little complicated, just say no and go with preemptive multitasking. I mentioned that we need to define priorities for tasks, and there are generally two ways of doing that, statically or dynamically. With static priorities, you define priorities for each and every task at design time. You can do it by deadline, so the shorter the deadline for the task, the higher the priority. You can do it by period. If the shorter the period, the higher the priority. Or you can do it by importance of a task, whatever is your definition of importance. This is simple. Simple to define, simple to implement. There is very little overhead. You have, after all, hard-coded everything. The latency for high priority task is minimal. But this system, as it is static, it's inflexible. And also it's suboptimal. In terms of analysis, that means that you could define a better scheduling that utilizes your resources better analytically. I will show you one example of static priority scheduler. This particular algorithm is called rate monotonic scheduling. And this is scheduling by period. The shorter the period, the higher the priority. We have 3 tasks, red, yellow, and green, and those arrows are deadlines. For the simplification, they also mark the end of the period for every task. And as red task has the lowest, the shortest period, it has the highest priority, it runs first. Then we have yellow task with a little bit longer period, it runs next, and finally the green task. This system is, as you can see, a little bit overestimated. We have some idling. Then we wait, as we already serviced this first deadline for red task, but when it passes, we run again the red task. And then after the deadline for yellow task passes, we do the yellow one, then red again, green again, red, yellow, red, green. Nothing complicated here. This is fairly simple. It's a little bit more complicated for dynamic priorities. Again, I will show you just one example. This algorithm is called EDF, earliest deadline first, and as the name suggests, it schedules by deadline. The shorter the deadline, the higher the priority of the task. In every tick of the clock of a processor, we examine which deadline comes first, and we assign priorities dynamically in runtime. This scheduling protocol is optimal. That means that we cannot find another more optimal, better scheduling analytically. But it's optimal only if system is not overloaded. I will talk about overloads in a minute. Just bear with me for a sec. This protocol also reduces the number of task switches, which is generally good because you don't have that much scheduling delay. But EDF deteriorates very fast and very badly under overload, and also it comes with a price. As you don't have hard-coded priorities anymore, you need to have a scheduler that will calculate them in runtime, and such scheduler is more complicated, smarter, simply more expensive. How does it look in practice? Again, we have this red, yellow, and green tasks and deadlines. Red deadline at 4 comes first. So the red task gets the highest priority and it runs. Then we have this deadline for yellow task. We run yellow task. And then we have those two. As we are probably in time unit 2, just after yellow task has finished its run, we're still waiting for the period and deadline of the red task to pass, so we will run the green task. Then red, obviously, just after the deadline passes. Then we have those two, still waiting for the red one, just like the last time, so we run the yellow one, then the red one. Then we have those two, so we will run the green one as we are waiting for the red one. the red deadline to pass, we do the red one, and finally we have this deadline and yellow task runs. This is a little bit more complicated. This looks complicated, non-obvious, and there is a general issue that comes with priorities. Dynamic or static. This issue is called a priority inversion. Let's imagine we have a space probe and we send it to Mars. And this space probe has a sort of information bus, a shared memory area which is used to pass information around the spacecraft. You can publish something on this information bus. And we have a high priority bus maintenance task which takes the data away from this bus and puts it on the bus. And we also have a low priority task which does the weather, looks at the Mars temperature and wind and other conditions, and publishes this weather information on the information bus. Let's imagine a situation where we gather the weather running and then we try to publish it on the bus. The access to this bus is exclusive. When someone is writing on the bus, no other entity can access the bus because we don't want to have an inconsistent state of the bus. So we lock this bus for exclusive use. And we start writing. But then high priority bus maintenance task is ready to run. So it preempts low priority task, does its startup, and tries to acquire a lock on the bus. It's not possible because the green task, the weather task, is using the bus already. And we cannot brutally take this resource away because we will get an inconsistent state. So the red task, the bus maintenance task, has to wait till green weather task, although it has low priority, uses the bus, releases it, and then the task switch can be finally performed. The lock on the bus is immediately acquired by high priority task. It runs, it releases the lock, does its post-mortem, and then the green task can continue. You see what happened here? This is called priority inversion. And priority inversion happens when high priority task is blocked in acquiring a resource by a low priority task and has to wait till this low priority task finishes using the resource. This particular kind of priority inversion is called bounded priority inversion, and it's a phenomenon. It's not necessarily a problem, but it can be a problem if it's unbounded. Let's say our spacecraft has an additional task, a medium priority task, which does communication with Earth. And it does not use this information bus. And let's come back to the situation where the red high priority task already experienced priority inversion. The green task is running using the resource. But suddenly this yellow medium priority communication task starts talking to Earth and talks and talks and talks, and both green and red task are waiting for this yellow to finish before they can continue their operation. This particular priority inversion is unbounded, and everything works fine most of the time. However, very infrequently, it may happen that this communication task runs so long that the system watchdog notices that, hey, this red high priority task is not running for quite a while now, and this probably indicates that there is something wrong with our system. So we need to do a reset. The unbounded priority inversion happens exactly like that. Medium priority tasks preempts low priority task that is using the resource, and on this resource, someone with high priority is waiting. And this is dangerous because potentially this high priority task can wait forever. If another medium priority task comes before this medium priority task finishes, you still wait. You still have to wait. And again, another can come. You can wait forever. That's why we implement watchdogs. Why I was talking about this space probe? Because this actually happened to a space probe, this one. Well, not exactly this one. This is a model in a museum. A model in a museum, not a model in studio where we faked this all. This is a Pathfinder probe. It landed on Mars on July the 4th, 1997. This was a peak of modern engineering obtained by most basics of hardware. There was a small processor inside, 128 megabytes of RAM. There was a fax modem, 2400 baud just for communication. It was fantastic. The mission was jeopardized by a software bug, which happened exactly as I described. There was an information bus, a communication task, and a weather task. And before the team on the ground was able to patch the system, the probe resetted 4 times. And funny thing, they actually reproduced this bug on the ground before probe launched. As it was a transient bug, they ignored it. And they ignored it also because the priority was on fixing the bugs in flight control software. But after a while, the problem was reproduced, fixed on the ground, and the software patch was sent to Mars. This patch implemented something called priority inheritance. It is a clever trick. If we have a low priority task that is working on resource, while it's working on resource, its priorities is elevated to the highest possible priority of the task that can wait on this resource. In our case, this green task, when it acquires a lock on the information bus, it runs with high priority, just like red task. Of course, when it stops using the resource, the priority goes back to normal. That way, this medium priority task will never run while the resource is in use. This protocol is not a silver bullet. It may have some adverse effects too. I will not dwell into details. Let's move to another topic. I've mentioned something about overloads. Actually, there are 2 terms, overloads and overruns. We say that the system is experiencing an overload when the computation time demanded by a set of tasks, a group of tasks, in a certain time interval exceeds the available processing power in this interval. And we say that the task experiences overrun if it exceeds its expected processor utilization. So the overload is on the entire processor, and overrun is for a single task. And in general, a single task overrun is not something catastrophic, but overrun on multiple tasks or overruns on tasks that continues in succession may have adverse effect on the system. And performance degradation is the best case scenario. Worst case scenario is system crash. The main cause of overloads and overruns is bad design. You have had a failure of imagination. You haven't noticed that something can happen. Of course, you can experience a hardware failure or unexpected arrival of events or unexpected input or unexpected change in environmental conditions. But this is just a nice way of saying that you have a bad design. Oh, there is one more thing, electromagnetic interference. Cosmic radiation can do a random bit flip on your hardware. But in general, this is a bad design. I will show you an overload condition, a transient one and a permanent one with a different scheduling algorithm. First, the transient overload, as the name suggests, this is a temporary situation, and an example is with earliest deadline first algorithm. You know the drill. We run the red task first, as the deadline of the red task is the nearest one. Then we do yellow task. Then we do green task. Right now, the green task has the highest priority because we waited for the red task deadline to pass, so it doesn't matter. But it experiences an overrun. And it misses its deadline. The red task cannot run because the green one has the highest priority. When finally the green task finishes, we have this deadline. This is the red deadline. We already missed one. Red task runs. But look, this green task having an overrun caused not only its deadline to be missed and the red deadline to be missed, also the effect is that we missed this yellow deadline. It has a cascading effect on the system. Of course, if no further overruns are experienced, the system will stabilize finally. But there is something that is more dangerous, and this is a permanent overload. This is a permanent overload example with rate monotonic scheduling. Let's start with red task. It has a computation requirement of 2 time units. It runs for 2 time units. Then we have yellow task, and it has computation requirement of 3 time units. It runs for 2 time units first, but then the red deadline passes, so the next period of the red task starts, and as red task has a higher priority with this scheduling algorithm, the red task runs for 2 time units. We missed the yellow deadline. Still, we have to finish our computation, this remaining 1 time unit. Right now, the yellow task will be run again because we are waiting for the red deadline to pass for starting another period. We run for 1 time unit, and then red task, the higher priority task, runs for its 2 time units. Then yellow task finishes its run with 2 time units. This time, haven't missed the deadline. Yay! Then the red task runs and the dance starts again. We will miss this yellow deadline, but I don't know if you noticed. We haven't run green task at all. This is a permanent system overload. Green task never gets the chance to run. What can we do with an overload? Handling overloads starts with handling overruns. So we can simply kill the task if it experiences overrun. Of course, sometimes it's not possible because the task is using the resource. We don't want to have an inconsistent state, so a more flexible way of dealing with transient overloads is allowing tasks to continue, just lowering its priority. There is one more clever way of doing that. This is called resource reservation. This is a technique that assigns slices of processing bandwidth to each and every task. And this slice assigned is just enough to satisfy computational requirements of particular task. If one particular task experiences an overrun, well, bad luck. But this does not have an effect on the entire system because the tasks run in isolation. Of course, it depends on your system whether you can use this technique. If you have task precedence, an overrun on one task will have an effect on other tasks too. Dealing with permanent overloads is, of course, harder. First technique is called job skipping. It's a clever way of saying that we will be killing, aborting some tasks, but we will do it properly. We will still guarantee that some jobs will be executed. that we will guarantee a minimum number of jobs per tasks to be run in a defined period. It can be done for a set of periodic tasks, providing your system is a soft or firm deadline system. This, for example, suitable for systems that process video. If you skip one frame every now and then, it's okay. It still looks fine. But if you process one frame and you are delayed, you get a choppy video and it's not desired. Another way of dealing with permanent overloads is called period adaptation. You have a set of periodic tasks and you just enlarge their period. You don't run them quite that often. Again, this can be done if your system allows for it. The third way of dealing with permanent overloads is called service adaptation. And in service adaptation, you deal your precision of the results returned with performance. So first, you perform an approximate calculation on your task, and then if you still have processing power, you can refine it. Obviously, this can be only done if your system is designed in such a way that allows for such service adaptation. In general, permanent overloads are hell to deal with. And there are so many techniques and so many problems and challenges I've described. And we need a way to deal with them all in order to say whether our system works or not. And this technique, the set of techniques for proving that our system works is called schedulability analysis. In general, we must do evaluation, testing, and verification of our system, working on worst-case execution time of any task in order to prove that our system is schedulable. Schedulable means that you can run all the tasks, you can meet all the deadlines. And it's not an easy thing to do because our analysis, theoretical analysis methods are limited. It's not like we just have one or two. No, there are a number of different analytical methods, but they do not scale well. If you have a small system, just a couple events serviced, just a couple of tasks, you can do pencil and paper mathematical proof that your system works properly. But if your system is complicated, this is just impossible. Those calculations you do on schedulability analysis are normally NP-hard problems, and it's simply not possible to do them in reasonable time. That results in restrictions when you have things that are really safety critical, mission critical. Safety critical systems are restricted in terms of hardware, in terms of software, and they are restrictive in terms of complexity. Safety critical systems are simply small. They sometimes even don't have an operating system. Just an infinite loop where you have just a couple of tasks and you service a couple of events. That way you can prove analytically that this system will work. All right, we are almost on top of the hour and I feel like I just scratched the surface. Let me give you a quick real-time summary. Why should you care about all that? First and foremost, I would like you to remember that in computing, real-time is not really real-time. And real-time systems are everywhere and challenges are everywhere. Fortunately, we have solved them all successfully, or at least mostly successfully. But there is still a lot of work to do. You see, Safety critical things are few and far between, and there is a large body of academic work on the subject, but very little industry uptake. So let me finish with call to action. If you are young, or at least willing and able, double in real-time systems. There are many things, many challenges to solve in both theoretical and in practical area and in between. It's fun, it's challenging, you will have a lot of satisfaction. Thank you very much for attention. See you next year. Stay safe.
Thank you very much indeed. Thank you, Maciej. A great insight into red, green and yellow sometimes. So this was Maciej Norberciak. We'll take a short break now, but don't go away. Get ready for our last talk of the day and later for Hack Dive, our virtual escape room. This is Code Dive 2021. So, our last speaker today is Kamil Witecki. Kamil is an experienced architect and chief engineer at Nokia. He can program in a plethora of languages, but normally sticks to C++ and Lua. He has so many interests that he can hardly focus on just one. So he loves literature and abstract humor and also plays the guitar. He has recently developed a taste for a healthy lifestyle. You may remember Kamil from so many previous code dives. There was no way he was missing it this year. So, Agile versus waterfall. Are these oil and water? Kamil, the cyberspace is yours.
Thank you very much for introduction. Yes, I'm Kamil Witecki. Welcome to my session at Code Dive 2021. This year we are doing it online. The session will take around 45 minutes. Should you have any questions, there will be chat box or Slack somewhere that you can use to ask me. And I will be there online having direct conversation with you. And I consider this is quite a good thing because we are no longer limited to simple yes or no questions, but we can have actual interaction and exchange our opinions. And this year, I would like to tell you how I see decision making and approach to methodologies in computer science, in projects. And before we'll go deep, few disclaimers. The presentation is intended for educational purposes only, and the views and opinions I will be giving you are my own. They are not endorsed, authorized by Nokia or any person or institution it refers to. Having said that, why I want to tell you what I think about architecture, what I think about decision making? Well, I have seen plenty of different videos, plenty of different trainings that were using some tricks to polarize the audience and telling us that one is ultimately bad and the other one is the one you should be using, the one that is your holy grail. And I disagree, because each and every option might have something good for you, and it will depend on the project you are working with that you will need to figure out how to approach it. How it usually works is that we have some kind of a sales speech. For example, in 20th century, if I remember correctly, or beginning of 21, there was Get Mac campaign by Apple. And it was brilliant piece of an advertisement. I really appreciate it. The problem with it, it's advertisement, and this kind of approach I do not accept in trainings. Meaning we have two different persons there, and they will have different traits. First of all, it will work on very simple biases like physical looks. Other than that, we will have some other traits that are not so obvious. So one person will be that shy person who cannot keep an eye contact, looks a little bit distracted and anxious. And in general, that might not be the most trustworthy person on earth. And there will be this other person, this very confident, sharp, someone with a plan and who makes all decisions just in time. And obviously, that person has everything in control, and the whole universe works for that person. So having said that, having established what traits these persons will have, somebody will now assign labels arbitrarily. So if I will be giving you Agile speech, well, I would assign the labels this way. The Agile guy would be confident, focused, just in time, and razor sharp, because he makes these decisions on a spot. There is functionality to decide about, and this guy just jumps in, makes the decision, saves the day, and goes for a beer with a team. And the insecure guy, that will be obviously the waterfall guy. Nothing stops me from assigning these labels vice versa. So I could simply swap these labels and tell that waterfall guy is the guy with plan. He is the one confident because he has planned everything. He's focused because he knows what he has in his control. He's just in time or even ahead of time, what arguably might be better. And last but not least, he's razor sharp. He knows what he's working with. He has budgets. He has everything planned. Nothing can surprise him. Do not fall for this pitfall. It just some way of selling. It's not necessarily best for decision choices. You will be better enabling your critical thinking and selecting what is good from both worlds. And I want to present you third option, something that I am using, and hopefully you will find some value in it. You will find it worth your time, and maybe it will help you become better at what you are doing. And so, I will have 3 messages for you, 3 things I want you to remember. If you should leave that speech with just 3 things to remember, this is it. Your decisions will cost. That cost will be paid either today, or you will have to pay it in future if you have to change your decision. And that cost will determine how important your decision is. The bigger the cost, the bigger the importance. Second of all, what usually is not told in methodologies trainings that I have seen is that the world is not only about use cases. Yes, customers are interested in use cases mainly, but there are also different things, orthogonal in that sense, that we need to take into account, and that's environment. So some kind of a box that we will be targeting, and that box will have some constraints. We do not have unlimited resources. We need to take into consideration the environment. And development aspects, business aspects. We have some company, we might need to scale it one day, we might need to introduce new products, we might change something, we might need to replace obsolete devices. This will be about development aspect. The world is not only use cases, it's also environment and development. And last but not least, urgent is not necessarily important. For example, when you wake up in the morning, the very first thing you wanna do is go shopping and buy some bread for breakfast. Simple as that. That decision is urgent. You need to decide now what kind of bread you will buy or what you will wear going to that shop, because you want to eat breakfast. There is some hard deadline. You do not want to eat your breakfast in the evening, obviously. It is urgent in some way. This is important if you will go there in a tuxedo or tracksuit. I doubt. In my opinion, that decision is urgent. It's not important. Do not let others tell you otherwise. And if somebody tells you you have to make that decision because it's urgent, well, maybe it's urgent, but maybe it's not you who have to make that decision, because it might not be important for you. Okay. Now, few examples of things that I would like to always consider in a project. And this isn't exhaustive list. There will be different aspects that you will need to consider and plan ahead. This is something I would like you to keep in your mind and at least check if that is a factor that plays major role in my development, in my company, in my project. And I would like to start with latency. Latency is about how fast I get a response to given request. And it will differ from project to project. We'll have very constrained projects, for example, telecommunication business or automatics and robotics, where we will have hard deadlines. If we miss that deadline, the whole work that we did is worthless. We will not make a call, we will break the robot, whatever takes. We need to meet the deadline. And there will be different kind of projects, like web applications. You send a request, you get a response, it's rendered in your web browser, and you can set up some budget, for example, 500 milliseconds for that round trip. Yet, if you miss it, nobody will make a problem out of it. The user will somehow swallow the fact that he got that response, that the page rendered after 1 second. So this limit is not that hard, it's soft, it's relaxed. If you will keep consistently missing it, like every request will be delayed, or you will keep missing it by a big margin, for example, it will not take 500 milliseconds, but 10 seconds, then yes, it's a problem. But you have some degree of freedom, and as long as 90% of your requests, and that's arbitrary number that I just made up, if 90% of your requests are done in time, you will be good with it. So latency, please consider it. It is not necessarily a factor for your specific case. You might be having this kind of relaxed requirement. It is always there. If you have listened to a presentation by Maciej Norberciak, he has some compelling point about everything being real-time system, and I recommend watching if you didn't done it yet. Latency is one thing. Another thing are the resources in general. So we will have memory, RAM or flash, CPU, and bandwidth. And with these resources, again, this might be hard constraints. We will have just given amount of RAM and we cannot use anymore. For example, we have an embedded device. It's a box, it has some RAM soldered in. There is thousands or millions around the world, and we need to write new software for it. We need to meet that budget. And that's it. We have 768 megabytes available. There is no magic to increase it. We might compress it, yes, but the limit is the limit. And if you are working in this kind of environment when you have this very strict, hard limitations, you might consider setting a little bit lower threshold just for yourself to learn early that you are approaching that boundary. And the same will apply to flash, for example. Your binary sizes will grow, and one day you might not fit them anymore in that device. CPU cycles or bandwidth of integrated network controller. On the other hand, you might be working with a cloud project, and cloud project arguably has infinite resources. You can just buy more RAM or more CPU or more disk space. It is virtually infinite, but in fact, you are doing some business. And your customers who will be paying for that cloud will not want to pay infinite money for your infinite RAM usage. So this will be now not anymore about environment where you work, but it will be about your business. Are you able to provide more value than your competition for the money they spend? Now, we have changed the axis. It's no longer environment. It is more relaxed because we can optimize. I will use a little bit more RAM, but I will deliver way more value. Still, we need to consider it. It's not infinite, but it is not as hard as in embedded devices where you have hard limits and you cannot change it. And another thing that will require you thinking about it if it needs your planning is compatibility. You might be working with kind of a project that I like to call torpedo projects. You just have the project, you finish it, somebody accepts, you ship it, and you forget about it. And it's cool. You do not have to think about compatibility whatsoever. It doesn't exist. That project is gone. It was one in a lifetime story, flash in the pan. There will be other projects that will last ages. Some projects are maintained for half of century now. And if you are working in this business, it will be a big deal to keep compatibility. There will be a lot of devices, a lot of applications working together in one way or another as an intricate puzzle, and some pieces will fall out. Some pieces will get obsolete. Your piece might get obsolete. So whenever you will be replacing that device, you want to create something that is compatible with the rest of the system. If it is other device falling out, you need to be ready for these signals from the future that you will need to interpret correctly, or at least not panic when you receive something that you don't understand. On the other hand, one day your device might get obsolete, and it will need to be replaced, and somebody would like not only to replace it as exactly same box, because then it will provide no value. Somebody will want to provide new features and will need to fit in the boundaries that you have created back then. Backward compatibility and forward compatibility in this kind of business will be crucial. And last but not least of the examples I want to give you is a programming language. And there will be different factors related to programming languages. They will let you optimize different things. For example, you can go for C++. If you have access to programmers and you need to control memory allocations and you are aiming for real-time, hard real-time requirements, that might be a good choice for you. On the other hand, you might go for Python, Lua, JavaScript, anything like that, if you want to have access to bigger pool of programmers, to something that is easier to introduce somebody to. And with JavaScript and Python, you might have hard time with predictability of garbage collection. Lua, on the other hand, it will probably not have that many users, at least from what I observed, it is not very popular language, but it will give you best from both worlds. It's simple, it's scripting language, it might be just in time compiled, and it gives you control over garbage collection, so you can have that predictability. And having that considered early enough might save you from rewriting your whole code base from scratch. And it happened to me that I was involved in a project that selected not so well-suited language for execution. We managed to deliver. It was a success story in the end, but the journey to get there and meet all the real-time requirements that we had in the meantime with that unpredictable garbage collection, that was quite a challenge for everyone. Consider these things. They might not be a problem for you today, but one day you will be in a project when that might play a role. And another thing is this development of your company. Because if you select the language that you and your friend love, it's cool, you wanted to make a project out of it for a long time, you start company, you are CEO, your friend is CTO, but in fact you're just programmers with fancy names. You develop your first version, you demo it to someone, and he invests. And the person invests big. You get a lot of money, you now need to scale that business. You need to hire 100 programmers and go fast. And it turns out that in your vicinity, you two are the only people who like that programming language and nobody else uses it. You will have hard time then scaling your company. That's different aspect. And maybe there are languages that become popular very fast, but if you need to scale your business one day, be sure you have people to source. So this is my list of examples. By no means it's exhaustive. If you have some ideas, use that chat box, use that Slack, and let me know what comes to your mind. I might learn something from you as well, and I will be grateful for that. And now an example of counter arguments that I hear often when talking about it. And it is just a matter of optimization now. Of course it is. I will give you that. It is just a matter of optimization now. The deadline is tomorrow, and we need to reduce memory usage by half. Good luck with that. It's just optimization now, but it's a lot of work. So it is not that simple. And you cannot guess right latency or right memory usage for each step either way. I will give you that too. I have no idea how each and every use case in system will work, and I have no idea how much memory or latency budget they will use. And due to that, I will not ask you to guess right. What I will be asking you is to have some high-level picture. You have some system, and you will need to decide how much memory you have. If you have embedded device, it's simple. It has the 768 megabytes of RAM available. Some part goes to operating system. That's a must unless you do it bare metal. And then you have some for your application. You go a little bit lower to have some safety margin. That's your budget for your whole system, for all the applications that you are deploying. Simple as that. If you know more or less what pieces will be there, I don't know, database, front-end, back-end controller, then you might split that budget between the applications, but do not go too far. You do not want to micromanage these things. You do not want to have plan for next few years. We are taking from waterfall here what is good for us. We are taking this more or less view on the big picture and setting up CI so that when you develop functionalities in an agile way, you learn quickly if you are going out of budget. And this way, you can start optimization just in time. The last argument that I'm hearing is that you do not need to pay that optimization cost just in time, because if you wait until end of the project, you need to apply just the right amount of optimization. You need to just optimize enough to fit that box. And it's very, very, very good argument in different world. Because in this world, optimization is not just something that you add on top or subtract. It's not like cutting a fat. It's like losing a fat on a person. It takes running, it takes new diet. And in case of optimization, it might take changing crucial pieces of your system. For example, it might be that the database that you have selected in the beginning is using too much memory, and now your whole application depends on that database and data structure exposed by it, and you need to overhaul everything. The problem is that if you had that CI setup back then, now you wouldn't be in that problem. You would have detected it earlier, and you would generate less debt. Yes, you would still generate some, but less, and you will react faster, generating less debt, having faster feedback, and giving that feedback to your planning people so they can have proper relations with customers, engaging them early that, hey, we have some kind of an issue that we need to mitigate. If you learn just one day before deadline, there is little room. Customers are expecting that software tomorrow. If you start engaging them early enough, you too can have meaningful discussion about mitigation actions. So adding just right amount of optimization on last day sounds cool, doesn't work, not in this world, really. Unless you are very lucky, and if you are very lucky, let me know. I would like to play Lotto with you. Now an example of a project where all this will not be a big deal. If you are doing batch processing of, for example, movies, it will take weeks or months to render the whole movie. And if you are concerned about latency and predictability in that case of project, I doubt. Because one still frame might take 47 seconds to render. Next still frame that has exactly same content will take 48 because garbage collection ran during that specific frame, and nobody will notice. In the end, that whole cost will be amortized and nobody waits for specific still frame. And the same will be about memory, CPU, all these other aspects. If you are working in cloud, you are doing this batch processing in cloud, you are generating a lot of value, you have huge budget, it might be just acceptable to use that more RAM, to buy it to render your movie. So this is kind of relaxed project where you can grab a cup of coffee and forget about all these things after you have thought if they apply. If they don't apply, enjoy your project. There will be different kind of projects and we will get to them at the end. Now I would like to give you some intel into how to approach decision making in such case. We had examples what to consider, but now how do I know it's important or urgent to make that decision? Well, let's get to it. First of all, what is important is seldom urgent, and what is urgent is seldom important. Dwight D. Eisenhower said that, or is associated with that quote, and it simply means that if something is really important, you would rather make the right choice and use more time to gather more data to be sure it is the right one, because the cost of changing that decision will be huge. And if something is urgent, obviously now, if it is urgent, it is probably not that important, because it's more important in that case to make that decision quickly rather than make the right choice. There will be also cases where it is both important and urgent, and not important, not urgent. So how to play around it? Well, we have so-called Eisenhower matrix. It is a tool from time management, And it is a tool that we will be using for our decision making too. We have important and urgent on two axes, and of course something might be important or not, or urgent or not. And now wherever our decision fits in that quadrant, we will do different thing about it. If it is important and urgent, this is something for you to own, to act, to do it right now. This is important, meaning it requires your attention, and it is urgent, it cannot wait. Act. Then we will have things that are important, not necessarily urgent. You have your time. Plan it. Find people who might give you second, third, fourth opinion, another point of view on it. Gather the data. Find a slot in your calendar where you will actually approach that decision. Gather all the intel in the world to make just the right choice. Urgent, but not important on the other hand, is something that you would like to delegate. First of all, you want to have more time for important stuff, and that is your own selfish thing to do, to optimize what you work with. Then it is also an opportunity for others, so don't be opportunity stealer. Let guys who you delegate it to gain something from it. They might, for example, by making the decision by themselves, optimize their workplace. They will select a tool they are comfortable with, select a tool they like to use, or select the one that optimizes their workflow. Or even if they cannot select something they like, they will have an opportunity in learning, in decision making. Maybe this will be the time when they will consider going to lecture like this one, because they would like to learn how to make good decisions. Or they already know it and they will learn to own the decision. They will learn that accountability. Do not strip them from that opportunity, delegate things. Last but not least are things that are not important and not urgent. And I said last but not least, but actually they are the list. This is things that you want to remove, you want to forget about them, do not waste time on them. And to me, one thing that always falls in that quadrant of not important, not urgent, someone down there, ideally nowhere, is tabs versus spaces. A discussion that is alive for such a long time, and I would like to use it as an example of both not important and not urgent things. And if you disagree, it's fine. Chat box somewhere there or Slack somewhere there. Let's have a discussion on it. If I don't convince you, maybe you will convince me. I feel I already used too much time speaking about it, but we will get back to it in a minute again. So the problem now is we want to work in that quadrant of important and urgent most of the time. And if we have something important but not urgent, we want to postpone it until it becomes urgent. So we want to plan it somewhere in our calendar. How do we know if it's important or urgent? This is the question. Knowing technique is one thing, but knowing how to actually weigh your decision and figure out where it fits, that's another story. And the problem is there is no yardstick that you just put to your decision and yep, it scales 10 on my yardstick, so this is it. There is no such thing. And I will not give you ready-made answer like a checklist. If this is this, and that decision is important, or these decisions are important, these are not. Unfortunately, maybe such thing exists, but I don't know it. If it exists, let me know, chat box again. And if it doesn't exist, I have developed some other system to weigh my decisions. And to me, urgency and importance both are some kind of a spectrum. So this given thing might fall from not until very important or very urgent. We will start now with urgency. Things will be not important, not urgent or important, and not important things are things that are just a matter of convenience, things that are just a matter of taste. And you see how I am going back to this tabs versus spaces again. It is just a matter of taste. you will never satisfy all people in the world. Somebody will tell you that they want tabs because of their own reasons. Somebody will tell you that they want spaces because of their own reasons. That guy will tell he wants 2 spaces. Other guy will want 4 spaces. Somebody will want 8 spaces, and you will never agree because it's just a matter of taste. And there is probably not that urgent to find out a solution. You will not satisfy everyone. You want to figure out things that are urgent. And what is urgent are things that will be blocking any progress in your company, or the ones that will cause major net losses due to delay. For example, you approach a milestone where you have to select the database. And if you do not select database, no work can be done anymore. So your company stops producing value until you make that decision. It is urgent now. Or there are major net losses. So somebody comes to you and tells you, no problem, take your time. It's just you have these contractual fines. If you will not make that decision, it's okay. We will swallow it. You will just pay us $1 million for every day of not making that choice. This is urgent too. There is real money behind it. You are either not generating it or you are losing it. But there is some cost involved, and it is urgent because the sooner you make that decision, the sooner you start generating or the sooner you stop paying. Do we get it? Urgent, blocks any progress, or causes major losses if not done. So how about important? Again, a spectrum. Not important, too important again. And what is not important is things that have virtually no long or short-term impact. Meaning, if you make that choice or that choice, things will be more or less the same. And costs will be the same, and quality of work will be the same. So there is no impact. You made some choice, but whoever can tell from external perspective, if not, then it's not important. Or you make a decision, it has big impact, but it has virtually no cost to change it. So you can make that decision today. Tomorrow you might change your mind. Oh, right, we went left. You know what, guys? We go right now. But it costs us nothing, so it's not a problem, really. Again, back to tabs versus spaces. Clang format, A-style. Every afternoon or every midnight, you can run Clang format and change it tabs to spaces. Odd days, tabs. Even days, spaces. Tabs, spaces, virtually no cost of change. Yes, there will be some CPU time. There will be some delay when the code base is changed, but it virtually has no cost of change. If you want, you can even run it on your personal PC. If you disagreed with the whole team, they have bad taste, but you had the good one, and they selected tabs, for example, you want spaces, you can be running it in your own PC, have that comfortable working conditions for you. And then before you commit, you just run it again, this time with different set of rules that will convert again to the spaces that you decided but you don't like, so you use these tabs. So it has virtually no cost of change associated, and therefore it's not important. You can guess now what will be important, and this will be things that will require overhaul of whole code base. So you need to scratch everything you have produced, waste it, and start over, or there will be huge penalties associated. And again, personal story. In one project I was working in, a decision was made 15 years before I joined that we will use some inter-process communication library. And now, after all these years, we have realized that we pay a lot in license fees, but we do not get any value from that library anymore, and it becomes ball and chain for us. It drags us back. So what we can do about it now? If we put legal, moral, and ethical aspects aside, we have at least 3 options. Keep paying for it, obvious, or stop paying for it but still use it. That might be a legal issue and ethical and moral. That's why we put it aside. And third thing, resign from it, but since whole code base was written around that IPC library, now we need to overhaul this whole code base. It was a tough one, and we finally made a decision around it, and it was the legal choice, so we are still paying for these licenses while overhauling code slowly but steadily, not to disrupt anything. But in the end, there were two decisions, and both of them were important. That decision of ours was important because there could have been penalties associated, or it would require overhaul of whole code base. The first decision done 15 years ago was important as well, because cost of changing that decision now was huge. So your decision that you take right here, right now, might have some probable impact in future. And I said probable because you have no idea if it will be changed or not. You need to take into consideration that probability of future changes, and if it's zero, then no worries. Even changing it would be very costly, but since probability is zero, then it means it will not happen, then it's not important. And if that probability is, I don't know, 75%, and it's very costly, then it means that virtually 75% of this cost will be paid one day. And this is important. So it's about probability of things happening in future that will determine what you should do about your decision. And obviously cost today will determine how you make the decision and how much time you spend on decision making. So this is important. Urgency was about things that might incur costs or might drag down your company if not done fast. Importance, on the other hand, are things that will require a lot of work, a lot of costs. Not necessarily today, might be 15 years in future, but that cost is there somewhere. Just to recap, we have these important and urgent things or not, and we want to do something about them. We want to work in that top left quadrant, the important urgent decision. This is the space where we act. This is what we want to be doing. If it's important and not urgent, we can keep postponing it until it becomes urgent. And this is the time when we make that decision. So just in time when it becomes urgent, find a time in your calendar, first of all, to do the research on it, and second of all, to actually make that decision. So this is the time I am making that decision. At this point, it becomes urgent to me because I decided so, and then it moves to this act quadrant. If it is not important but urgent, find someone for whom it is important, ideally, and delegate it. That person will have a benefit of optimizing that choice for the team, for the person, or whoever else, and will have an opportunity in learning. We might learn decision making, might learn accountability, delegate it. Find someone ideally for whom that thing is important, so for that person, this becomes act now type of task. And last but not least, remove source of concern. Tabs or spaces, things that we shouldn't be discussing, things that we ideally wouldn't be deciding about, or we will just toss a coin and let it decide for us. Remove source of concern in any way possible. If you can, skip it, skip it. If you can, make a random choice. And if I didn't convince you about tabs and spaces, right now Slack and chat box might be full of different comments, and I am waiting for it eagerly. And I promised you that there will be different kind of project that I will tell you about, and this will be medical business or robotics. In that kind of project, any error going out of latency budget or out of RAM might be a matter of life or death, literally or figuratively. And in this case, predictability of garbage collector will be important. If you stop that motor in precise time, it's successful surgery. If you stop it a little bit too late because garbage collection ran just before the signal was sent to the motor, it might be a tragedy. In case of this kind of projects, the stuff I gave you as an examples will be ultra important. On the other hand, if you are working with robotics, for example, you have numerically controlled laser cutting machine. If it crashes while laser is still on, it might never turn off that laser. You can imagine consequences. And with that strong message, I would like to close just to recap 3 things I would like you to remember. First, your decisions will have costs associated to them. The cost will be today or tomorrow. Either you will need to pay it or not. It might be some kind of probability associated to it. And last but not least, it will be big, it will be small. It's up to you to figure that out. The world is not only about functionality. Functionality is what customers pay for, yes, but environment and development use cases, how you develop your company and what box you are targeting, what are your constraints, this is something you will need to consider even if customer doesn't want to hear about it because for them it just cost. And last but not least, urgent and important, 2 different things. Sometimes they coincidentally are both a factor for that decision, but you will have a lot of things that are either not urgent but important or not important but urgent. Make sure you know where in the decision quadrant, Eisenhower matrix, that specific thing falls in so that you know what to do about it. Thank you very much for your attention. I'm Kamil Witecki. Here we end the conversation. Here we end the presentation. If you have any questions to me, use that chat box or an email address you have on the screen. That's all from me. Goodbye.
Kamil Witecki, thank you very much indeed. So, this is it for this year's Code Dive. This year we've had 14 talks, 2 streams, a very brave group of Nokians preparing the conference, 1 virtual escape room, 1 video crew making it happen for us online, and of course you, the one and only Code Dive audience. Thanks for joining. Don't forget about Hack Dive, our virtual escape room. The game is about to start on our website. My name is Rafał Motriuk. I'm a science and technology journalist. It was, as ever, a great pleasure being your host. Thank you for having me. Goodbye and see you again.